so I just get started here. So it's great to welcome Dr. Anson Deluso. He is currently a postdoc at the University of Washington in the astronomy department there. He's been there for about a couple of years now. He got his PhD in 2011 from Yale, and then spent 3 years as a postdoc at UT Austin before he went to Washington. So his research interests are in the fields of cosmology and theoretical astrophysics, and imaging theory studying structure formation and gravitational lensing and reionization, which is what we're going to hear about today.
Yeah, it's great to be here, and thank you, Janelle, for inviting me to talk. So today I'm going to be talking about some exciting new developments in the high-redshift Lyman-alpha forest and what they might tell us about the cosmological reionization process. And I'll start with some background. So in 1965, just 2 years after the discovery of the first quasar by Martin Schmidt, Jim Gunn and Bruce Peterson pointed out something curious about the spectrum of the most distant quasar known at the time. It's an object named 3C9, and it was distant enough such that its Lyman-alpha emission line was redshifted into the optical, such that it could be observed by ground-based telescopes. Although it was far from certain at the time, it was generally expected that most of the mass in the universe was contained in the intergalactic medium in the form of hydrogen. And so Gunn and Peterson noted that if even a tiny fraction of this hydrogen were neutral, then it would block all of the light blueward of the Lyman-alpha emission line of 3C9, as this light redshifted into the Lyman-alpha resonance in the rest frame of the gas. Even with the crude spectrum that was available at the time, it was clear that 3C9 did not display such a blockage. That would now become known as the Gunn-Peterson trough. So it doesn't have a trough here. And so Gunn and Peterson were led to conclude that if the intergalactic hydrogen existed at all, it had to have been highly ionized. And so this was a quote from their 1965 paper. It's always fun to go back and read those old papers and find out what they didn't know back then and what we now take for granted. As far as what did the ionizing of the hydrogen, it was too early for them to tell, but they speculated that the intergalactic medium was simply very hot and therefore thermally ionized. In 1970, Ahrens and McCrae came along and suggested that perhaps it was the quasars themselves that ionized the hydrogen. In other words, that it was energy released during accretion onto supermassive black holes that photoionized the hydrogen. And that remained the standard view for about 17 years or so. But by 1987, as measurements of the quasar luminosity function improved and not a single Gunn-Peterson trough had been observed out to a redshift of 3 or so, there were signs that the quasar population was dropping off too quickly with redshift to photoionize the IGM. And so in 1987, Paul Shapiro and Mark Giroux at UT Austin argued that the IGM had to have been photoionized by a yet undetected population of sources, perhaps the first galaxies. So since then, theoretical modeling and observations have improved significantly, and we now have a standard picture for how the IGM was reionized, and it fits very nicely into the cold dark matter cosmology. And so I'll describe that standard picture to you now. So in the standard model, the universe began in a very hot and dense state about 13.8 billion years ago. And about 400,000 years later, the primordial gas expanded and cooled to a temperature of about 10 eV, at which point the recombination of hydrogen became an efficient process. And so at this time, the gas went from being almost completely ionized to almost completely neutral. And so began the cosmic dark ages, in which this neutral gas cooled with the expansion of the universe, and pre-galactic halos began to form hierarchically, driven by the nonlinear collapse of dark matter. Now, in order to form stars, you need to cool this pristine gas of hydrogen and helium. So current models suggest that this began to happen about 100 million years after the Big Bang, within dark matter halos with masses of about 10 to the 5th, 10 to the 6th solar masses. So these halos are massive enough to have virial temperatures hot enough such that cooling by molecular hydrogen is an efficient process, so stars could form. But this early episode of star formation, what we call population 3 star formation, probably didn't last very long because these halos, these small, what are called mini halos, are highly susceptible to both internal and external feedback processes. So this star formation was likely quenched. So it's widely believed that the formation of the first galaxies had to wait later when more massive halos formed that could cool that were hot enough to cool their gas by atomic hydrogen. So in the standard view, reionization is driven by this generation of first galaxies. And at this time, ionization fronts, fueled by their ultraviolet starlight, swept out into the IGM, leaving behind hot bubbles of ionized hydrogen and singly ionized helium. And these bubbles expanded outward until they eventually overlapped, returning nearly all of the hydrogen in the universe to an ionized state before it was about 1 billion years old. As I'll discuss later, whether quasars played any significant role in this reionization process is still a topic of debate for some, and it has been a topic of debate for several decades now. In the standard view, the second reionization of helium, or the reionization of helium-2 to helium-3, had to wait until about 1 billion years later by redshift of 3, and we think that this corresponds to the rise of the quasar population, because the quasars can produce copious amounts of energy, photons with energies in excess of 4 Rydberg, which is what you need to doubly ionize helium. And so from now on, when I talk about hydrogen reionization, I'm going to just call it reionization. And when I talk about the second reionization of helium, I'll just call it helium reionization. So this standard view was assembled largely from theoretical modeling with some guidance from observations. But still, we know very little for certain observationally about reionization. That's because it lies just beyond the frontier of current observations. There have been a number of observational probes of reionization, most of which are pretty subtle to interpret because they're model dependent. And so I'm not going to discuss more about them here. So far, the most robust constraints come from the cosmic microwave background and the Lyman-alpha forest. So the scattering of CMB photons from free electrons that are generated during reionization generates large-scale anisotropies in the polarization of the CMB. And measurements of this large-scale polarization tell us that reionization was about halfway complete by redshift of 9 or so, roughly speaking. On the other hand, measurements of the Lyman-alpha forest allow us to place a lower limit on when reionization ended. And I'll talk more about that in detail in just a minute. So the Lyman-alpha forest provides our backbone for our understanding of the IGM, and it's the central topic of this talk. And so I'll give just a brief reminder of that here. So as light from a distant quasar travels towards us through the post-reionization IGM, it gets redshifted because of cosmological expansion. And from time to time, Lyman-alpha resonance scattering from residual neutral hydrogen in the cosmic web removes some of that light from the line of sight, creating these absorption features. And the series of fine absorption features, blueward of Lyman-alpha and redward of Lyman-beta, is called the Lyman-alpha forest. And the amount of absorption in Lyman-alpha forest is very sensitive to the ionization state of the IGM. So it's this sensitivity that allows us to place constraints on the end of cosmological reionization. So these panels here show some high-redshift Lyman-alpha forest spectra, where the redshifts are given here, of the quasars. At a given location in the forest, the fraction of the quasar's flux that's transmitted in the forest, F, can be written in terms of what's called the Lyman-alpha optical depth, tau. For a large enough patch of the forest, this optical depth scales approximately as the local neutral hydrogen fraction. But at a redshift of 6, the proportionality constant is very large, such that a neutral fraction as little as 2 parts in 100,000 is enough to block 99% of the light in the forest. So just the fact that most redshift 6 segments of the forest show even a little bit of transmission implies that reionization had to have been largely complete by that time. So we can put this into more quantitative terms by simply binning the forest into pixels a few megaparsecs wide and counting the fraction of pixels that are dark in the Lyman-alpha forest. This dark fraction of pixels actually translates to an upper limit on the global neutral fraction of hydrogen. So that's exactly what Ian McGreer and collaborators did. These arrows show upper limits on the global neutral fraction as a function of redshift. Now oftentimes you get no transmission in the Lyman-alpha forest, because remember I said it's very sensitive to the ionization state. But you get some transmission in the Lyman-beta forest, the coeval Lyman-beta forest. But note, if that pixel is truly neutral, it has to show up as dark in both the Lyman-alpha forest and the coeval Lyman-beta forest. And so the strongest constraints come when you combine the dark pixels in the Lyman-alpha and Lyman-beta forest. And that's what these purple arrows show. They're upper limits, and this tells us that the global neutral fraction of hydrogen has to be less than about 10% by redshift of 6, or 5.9 or so, at 1 sigma. Okay, so these constraints are still, still a lot of wiggle room here, and I think more wiggle room than most people appreciate. But quantitatively speaking, this is why we think that reionization had to have ended by a redshift of 6 or so. But the high redshift forest probably contains even more information about the reionization process. In fact, in this talk, I'm going to argue that it does. And so let me foreshadow a bit by pointing out something curious about the comparison of these high redshift quasar spectra. Notice how much the amount of transmission in the forest, averaged over large scales, varies from sightline to sightline. So for example, here you've got a 150 co-moving megaparsec trough with no observable transmission in the forest. Here you've got significant transmission over that same spatial scale. And I should note that this dark trough in the Lyman-alpha forest actually shows substantial transmission in the Lyman-beta forest. So the black and the blue curves here show the transmission in the coeval Lyman-alpha and Lyman-beta forests, respectively. So we know that this huge trough can't simply correspond to a large neutral region in the IGM. So it turns out that explaining these large coherent variations in the forest, in the opacity of the forest, is very difficult to do without some drastic change in the way that we're thinking about the forest. And so that's what I'm going to talk about here. Okay, so let's put these variations in the forest on a more quantitative footing. A typical way to quantify the opacity of the forest is to simply average the flux in the forest over a segment of length L. So these most recent measurements by George Becker and collaborators use this convention of L equals 50 H inverse megaparsecs co-moving. And this is sort of it seems like an arbitrary choice, but it's chosen to sort of maximize the fluctuation amplitude that I'm going to talk about later. But so I'm going to adopt this convention from here on. So you average the flux over that segment, and then by convention translate it to an effective optical depth, what I'll call tau effective from now on. Just keep in mind that this tau effective is just like a negative log of the flux. Okay, so higher tau effective means more absorption, lower tau effective means more transmission in these 50 H inverse megaparsec segments of the forest. So if I measure tau effective across different lines of sight and at different redshifts, I get this plot here on the right. So notice the steep evolution in both the mean and the dispersion of tau effective as you approach a redshift of 6. So remember, this dispersion just reflects those large-scale variations in the transmission of the forest that I talked about by eye. So this talk is focused entirely on explaining this rapid increase in the dispersion as you approach a redshift of 6. So where might this dispersion come from? Well, fortunately, the physics of the Lyman-alpha forest is pretty straightforward. As I said before, the optical depth scales approximately as the local neutral hydrogen density, which shortly after reionization scales as the ratio of the recombination rate over the photoionization rate. The recombination coefficient scales as temperature to -0.7, and the free electron and the ionized hydrogen densities each contribute a factor of gas density. The photoionization rate scales with the amplitude of the ionizing radiation background. And so the bottom line here is that there are 3 places from which this dispersion can come. It can come from fluctuations in the IGM density, fluctuations in the IGM temperature, and fluctuations in the strength of the ionizing radiation background. And in this talk, I'm going to touch upon each of these fluctuation sources. And as I do that, I'm going to highlight the term that I'm talking about in the lower left-hand corner so you can keep track of what effect that I'm talking about. So by far, the best understood piece of this equation is the contribution from the IGM density fluctuations, because we can simulate those on the relevant scales very easily. So a convenient way to visualize the dispersion in the opacities, or the dispersion in tau effective, is to plot its cumulative probability distribution, or the probability of measuring a tau effective less than a given value. So these histograms show the recent measurements of that distribution by George Becker and collaborators. The narrower the distribution is, the less the fluctuations, and sort of the flatter the distributions, the wider the dispersion. These dashed curves show a model that isolates the contribution from the density fluctuation. So this is like a density fluctuation only model. And what you'll see is that at lower redshifts, the density fluctuations do a good job of accounting for the opacity fluctuations. But as you get to higher redshifts, they systematically underpredict the dispersion in the opacity fluctuations, such that by redshift 5.5 or so, the discrepancy is considerable. And so the central problem here is that IGM density fluctuations alone don't seem to be enough to account for the large-scale opacity fluctuations in the forest. Okay? And so the remainder of this talk is on 3 potential solutions to this problem. 2 of the solutions invoke fluctuations in the ionizing radiation background, and one of the solutions invokes fluctuations in the IGM temperature imprinted during patchy reionization. And in particular, this model, if it's correct, if it's true, ends up having important implications for the reionization process.
There's no chance that the model is wrong. I mean, you're telling us the model seems to be perfect, and so this is you just ruled out. You said that you were able to model this extremely accurately. You see now a discrepancy between the model and what you observe.
Yeah.
But your conclusion is that there has to be some other explanation than the model is wrong, right?
Well, the model is a model that isolates one effect, right? So clearly the model doesn't have all of the physics that's going to generate the capacity fluctuation. And so what we're about here is really just sort of trying to figure out what physically is driving these opacity variations.
You understand little filaments so accurately in the model.
Yeah, well, because this is this is the IGM. This Lyman-alpha force is sensitive to modest underdensities, and so we're not sensitive to sort of the more overdense regions near the galaxy. If you're just talking about the fluctuations from the IGM density, you're not sensitive to sort of the astrophysics that's going on at the outskirts of galaxies that we don't understand well enough. Fair enough. But so for the density fluctuations that contribute to this effect at high redshifts, we think we know those pretty well. Fair enough. I mean, maybe there are some uncertainties in the modeling. On the other hand, I think that the uncertainties in the observations themselves are likely to be much greater than the uncertainties in the model of the IGM density fluctuation. So I think it's fair to say that, okay, maybe there could be uncertainties in the observations, which sort of make these conclusions a little weaker. But
uncertainties in the observations.
Yes. Yes.
Not in the models.
Not in the models. But I'm standing. My point of view is that
I'm an observer, so I believe that the universe is the way it looks and not the way it's modeled.
But even the observers will admit that there are some uncertainties. Like, for example, they have to take out the placement of the quasar continuum,
of course, yeah.
and they have to model that. So I mean, you're right. The universe is the way it looks, but then there are certain sort of model-dependent statements that they have to make, and there are uncertainties associated with that. So. I sort of stand by my statement that we understand the IGM density fluctuations very well for these overdensities. From a theoretical perspective, right? In the cold dark matter paradigm. Okay. If you're familiar with this literature, there has been a fourth solution proposed to this. I'm not going to talk much more about the solution because I think there are some technical issues associated with these conclusions, but if you're interested and if you're familiar with the literature, please feel free to ask me about it later. So I'm going to focus primarily on these three solutions here. Okay. So let's begin by considering the origin of spatial fluctuations in the ionizing radiation background. Okay, so these fluctuations are determined by the abundance and the clustering of the sources of the ionizing radiation background, as well as the mean free path of the ionizing photons, or roughly speaking, the typical distance that the photons travel before being absorbed in the IGM. At the redshifts of interest here, redshift 5 to 6, this mean free path is set by the typical distance to absorbers in the cosmic web with characteristic overdensities of 100 or so. So typically at the outskirts of dark matter halos. And these are what people often loosely refer to as Lyman limit systems. So in this cartoon sketch, the sources of the background are depicted by these blue dots. It could be galaxies, it could be quasars. And the mean free path is depicted by these red circles, such that these points, these stars in the IGM, only effectively see sources within their respective mean free paths. So you can imagine then that the ionizing radiation intensity here is greater than here, simply because this point sees more sources within its mean free path. So this sort of drives fluctuations in the radiation background. Note also, the larger the mean free path is, the smaller the fluctuations in the background are, simply because you're smoothing the source density, or the source distribution over larger scales. And you can see that in this cartoon sketch by noting that the difference in the number of sources between these 2 points in these circles is less than in this configuration. So smaller mean free path, larger fluctuations, larger mean free path, smaller fluctuations.
Is the mean free path here to absorption and scattering?
To absorption.
Okay, what about scattering?
Well, scatter. So that's right. That when a photon gets absorbed, it can be rescattered. And this is what's called recombination radiation. And some fraction of that will end up, not contributing. They'll be rescattered at energies that are less than the Lyman limit. And some fraction will actually be able to rescatter, to reionize a neighboring hydrogen atom. And what that ends up doing is sort of homogenizes the background a little bit, but the fraction of radiation that ends up escaping and doing that is a little bit smaller.
So resonance scattering is not important.
I'm sorry, I don't know what you mean. So resonance scattering, so these are ionizing photons, right? Their energies above the Lyman limit.
They can still scatter. So
Yeah.
I'll ask you.
Okay.
There's one thing I'm not quite following. So the mean free path, in principle, it will depend on the local density as well.
That's right.
Okay.
Yeah.
So, I mean, one
So-
of these circles would actually be larger than the other circle.
I'm going to talk about that in just a bit. Yeah, so that's exactly right. Okay, so it's on the next slide, right? Okay, so that's it. That's it for the background, and now I'm going to start to get into the solutions to this problem. And so let me. This first solution that I'm talking about, this model is due to Fred Davies and Steve Furlanetto, and it adopts the standard assumption that galaxies dominate the high-redshift ionizing radiation background. So quasars are not contributing significantly at these redshifts. That's the assumption that is adopted here, and there are models that break this assumption that I'll talk about later. In particular, okay, so this model postulates that the large opacity variations are driven by large fluctuations in the ionizing background from the clustering of the high-redshift galaxy population. And in particular, Davies and Furlanetto, as Ryan mentioned, emphasize the importance of modeling large-scale variations in the mean free path due to the interplay between the sources and the sinks of the ionizing photons. So in overdense regions where there are lots of galaxies, the local absorber population is more highly ionized, and so the mean free path tends to be longer there. Whereas in underdense regions where there are less sources, the absorbers are less ionized, so the mean free path is shorter there. And it turns out that these large-scale modulations act to amplify fluctuations in the ionizing radiation background. And you can see that by noting that in this overdense region, this point ends up seeing even more sources within one mean free path, and this point sees fewer sources. Okay, so Ryan's absolutely right. It's important to model these things. And actually, we do model these things now after this paper by Davies and Furlanetto. But okay, so there's a serious drawback to this model. And the drawback is that the background fluctuations have to fight the effect of the density fluctuations. So consider an underdense region of the IGM. If you're just thinking about the IGM density, this region should be a more transmissive region in the forest simply because of the lower neutral hydrogen density there. But in this model, the ionizing radiation background is greatly suppressed, both because it has fewer sources of the background, but also because the mean free path is shorter there. And this suppression of the ionizing radiation background would actually increase the opacity of that region. You can see that by noting that the background comes in the denominator of this equation here. And so what you need for this model to work is you need for the ionizing background fluctuations to be so strong that they overcome the density fluctuations and they invert the Lyman-alpha forest, making the underdense regions become the most opaque regions of the forest. And this is the opposite of what you would expect at lower redshifts when the density is driving the fluctuations, and sort of the less dense regions are the more transmissive regions, right? Whether you can achieve large enough background fluctuations to invert the forest depends on the value of the spatially average mean free path. Smaller mean free paths lead to larger background fluctuations and more of an inversion effect. Right? Just keeping in mind the discussion that I had earlier. But the mean free path has actually been measured out to a redshift of 5.2, where it takes in the value of about 60 co-moving megaparsecs. And if you extrapolate these measurements of the mean free path out to higher redshifts, at redshift 5.6, it takes on about 45 co-moving megaparsecs. And so I decided to look into this model in a bit more detail to see, can it really explain the tau effective dispersion given that we have constraints on the mean free path? And what I found is that making this model work requires spatially average mean free paths that are quite short. So for example, 20 megaparsecs at redshift 5.6, that's a factor of 3 less than the value that's been measured at redshift 5.2. And it turns out that there are physical issues with having the mean free path evolve by such a large factor in the 100 million years between these two redshifts. So those physical issues are a bit subtle, too subtle to get into here. But sort of the takeaway point here is that making this model work requires that these measurements, these highest redshift measurements of the mean free path, come down by a factor of 2 or so. And so already from these constraints of the mean free path, it appears that this model is in a bit of trouble. Unless the measurements of the mean free path are wrong. Okay, so the central question here is, can these highest redshift measurements of the mean free path be off by a whopping factor of 2? And it turns out that amazingly the answer, and I know probably the observers are not going to like this, but the answer amazingly is yes, they can. And so to explain why, I need to discuss how these measurements are made just a little bit. So these highest redshift measurements of the mean free path are made by stacking rest frame quasar spectra and looking at how quickly the flux declines at wavelengths blueward of the Lyman limit. This decay envelope here encodes information about the mean free path, and so you can measure the mean free path by fitting a model to this decay envelope. But quasar sightlines are very special sightlines in the universe, because the ionizing background along those sightlines can be significantly enhanced by the presence of the quasar itself. Okay? This is what's known as the quasar proximity effect. So how might quasar proximity zones affect the measurements of the mean free path? Well, remember that I said in regions of enhanced ionizing background, the local absorber population is more highly ionized, and so the mean free path tends to be longer there. And so it's natural to expect that the mean free path measured along only quasar sightlines is longer than on average. So the sign of this effect is correct in the sense that it would take the mean free path measurements and push them up from the actual value. So I did a detailed calculation of this effect, and what I found is that the mean free path measurements can indeed be biased, and by up to a factor of 2, where the severity of the bias depends on your model for the quasars. And specifically, on what time scale does the luminosity of the quasars vary. And so there's still a lot of uncertainty about the magnitude of this bias that is there. But what I've shown is that it can be important, and it's certainly not an effect that can be easily dismissed or neglected. And so the bottom line here is that, yes, the short mean free paths that seem to be required by this model are plausible, despite the mean free path measurements. And they're plausible because the quasar proximity effect could potentially bias the measurements by up to a factor of 2. But there's uncertainty in that. And so, yeah, so that's the bottom line. Now, I've been in contact with the observers who made these mean free path measurements, and they agree that this effect is, it can in fact be important. And they're actually quite enthusiastic about revisiting their measurements, and we're thinking about ways to disentangle these effects. And so stay tuned, I think we'll hear more about this effect in the near future. So for now, I'm going to label this model as plausible. And I want to briefly discuss what this would imply for the reionization process. So the photoionization rate scales as the product of the emissivity of the galaxy population and the mean free path of the ionizing photons. Or, said in another way, the global strength of the ionizing background scales with the ionizing photon output of the sources and the typical distance that the photons travel. So intuitively, if I decrease the distance that the photons travel, I have to increase the output of the sources if I want to maintain the same level of the ionizing radiation background. The Lyman-alpha forest photoionization rate measurements are not going to go anywhere from this effect. They're not affected by it. So if I decrease the mean free path by a factor of 2, I have to increase the emissivity of the galaxy population by a factor of 2. So if this scenario ends up being correct, I take all previous Lyman-alpha forest measurements of the ionizing emissivity from the galaxy population, and I bump them up by a factor of 2. So in other words, the number of ionizing photons produced per hydrogen atom per gigayear goes up by a factor of 2. And what this would imply is that for all other parameters being fixed, this would make the reionization duration shorter because of the higher emissivity. So clearly, probing or testing this model in the near future will have important implications for reionization. In particular, it's important to pin down exactly what the mean free path is doing above a redshift of 5. Okay, so now on to the second model that I'm going to talk about today. This model is due to Jonathan Chardin, Martin Hainault, and collaborators. So you can generate large fluctuations in the ionizing radiation background if the sources of the background were much rarer than typical galaxies. And you can do that without requiring a short mean-free path. Just make the sources rare. So in other words, what if instead of this kind of picture for the sources, you had this kind of picture? Well, you can imagine that the intensity at this point would be much greater than at this point simply because of the shot noise in the source distribution. The most sensible way to achieve this effect is to let quasars, which are much brighter and rarer than typical galaxies, contribute significantly to the high-redshift background. And so this model abandons the standard picture that galaxies dominate the high-redshift background, and it lets quasars contribute significantly. That standard picture in which galaxies dominate the high-redshift background is based on numerous measurements of the quasar luminosity function, which show that the quasar abundance is dropping off very rapidly with redshift above a redshift of 3 or so. And therefore, their contribution to the hydrogen ionizing background is dropping off rapidly. And these previous measurements actually exclude a significant contribution from quasars at the redshifts of interest here. But recently, some authors have questioned these measurements because of a relatively high, an unexpected high abundance of faint AGN reported by Emmanuel Giolongo and collaborators. So by looking for X-ray flux that's spatially coincident with high-redshift galaxy candidates, they identified a relatively large population of AGN at luminosities much fainter than previous surveys were sensitive to. So these red data points show their luminosity function measurements, and these other points show a collection of previous measurements at higher luminosities using different selection criteria. Because the number density of AGN of Giolongo is much greater than you would get if you just naively extrapolated the other measurements to lower luminosities, Giolongo actually suggested that the previous surveys missed a large fraction of AGN at intermediate luminosities. And if you believe these claims, then it could mean that quasars and AGN contribute more significantly to the hydrogen ionizing background than previously thought. So if you translate these luminosity function measurements to an ionizing emissivity, you get these points here. So not only would this require a complete revision of our understanding of the Lyman-alpha force, it could also potentially require a complete revision of our understanding of reionization.
So the figure on the left is like some convolution of the, say, luminosity of the quasar and number density, right?
That's right, yeah.
And
And
so
then
is
an
the-
assumption
they're not-
about the escape fraction goes in there as well.
Okay. But so the only thing that's changing, the reason that the red points on the left are much higher is just because they think they're missing numbers, and there's nothing like changing in terms of like luminosity per source or something.
Well, there's nothing changing about the escape fraction that's assumed, but yeah, you're right, exactly.
Okay, that's what it's, okay.
Yeah, so it's just the fact that you've got so many more quasar or AGN at intermediate luminosities that is driving this emissivity upwards. And okay, so in a recent paper, Maddow and Hart showed that if the ionizing emissivity from AGN follows this trend with redshift, that AGN can actually reionize hydrogen by themselves without any contribution from galaxies by redshift of 5.5. And so that would be a completely different picture of reionization than the one that I described earlier, in which the first galaxy drove reionization.
And so once again, that's just driven by like this number density, this number that's missing, not like any change in.
That's right, but the thing also, it's driven, the fact that they're putting the galaxy contribution lower is driven by the fact that you don't want to over-predict the background as well, because you have constraints of that from the Lyman-alpha forest. So if you let galaxies contribute, if you have quasars contributing this high, and you let galaxies contribute at the same level that they used to, you'll end up ionizing the Lyman-alpha forest too much.
So for this Giolongo thing,
Yeah.
so there's like diffuse or faint X-ray emission that is not, that people don't associate with individual quasars, but does seem to be spatially angularly correlated with galaxies as the redshift.
So they claim, yeah. Yeah. So this renewed debate, okay, so this is actually, for some authors, this has reignited the decades-old debate about whether quasars contribute significantly to reionization. People seem to like to argue about that. So prompted by this renewed debate, Jonathan Sardine and collaborators actually said, okay, well, what if this rare source picture is a more appropriate picture for the high-redshift ionizing background? And so they came up with a model in which more than half of the background comes from AGN, and they found that this kind of model can explain the large fluctuations in tau effective that have been measured by Becker and collaborators. So how might we go about testing this model? Well, the simplest way, or the most straightforward way rather, is to look for the AGN at intermediate luminosities that Giolongo said should be there. That's probably a little bit easier said than done. But there is a way that we can probe this model using data that's currently available to us. AGN are expected to produce, did I shoot you with the lecture? Sorry. AGN are expected to produce more hard photons than galaxies do. And in particular, those hard the photons with energies in excess of 4 Rydberg would doubly ionize helium. And the photoelectrons that are produced during this process would inject heat into the IgM. So these panels here show slices through a simulation of helium ionization by my collaborator, Matt McQuinn, where the panel on the left shows the helium-3 fraction. The red regions are the ionized regions. And the panel on the right shows the corresponding rise in the IgM temperature from the helium ionization. So because these AGN-heavy models would end up reionizing helium much earlier than the standard picture, they end up predicting IgM temperatures at redshift 5 to 6 that are significantly hotter than the standard models. And so one way that we can constrain this is to simply compare these models to the temperatures which have been measured out to a redshift of 5 from the Lyman-alpha forest. And so I decided to quantify the amount of heating that you get in these AGN-heavy models. And what I found is that any model in which AGN contribute enough to the background to explain the tau effective dispersion ends up being discrepant with the temperature measurements. So the panel here on the right shows the global helium-3 fraction in these AGN-driven models where the AGN emissivities are given by these curves here on the left, the same line styles. The panel on the bottom shows the temperature at the mean density of the universe as a function of redshift, where these data points are the measurements of Becker and Boera, the recent measurements. This, for reference, this red curve is this can quasars do it all model of Medall and Hart. And what you'll notice right away is that the answer to the question, can quasars do it all, is no, at least if you're considering consistency with the IgM temperature measurements. Also, even a model where AGN contributes just 25% of the ionizing background ends up being discrepant with the temperature measurement. What you really need to be consistent with these measurements is for the emissivity from the AGN to be dropping like a rock above a redshift of 3 or so. And so for this reason, I think it's going to be difficult to reconcile these AGN-driven models and these measurements of Giolongo with measurements of the IgM temperature. What you need for this model to work is for something exotic to happen in the spectra of the AGN, where you're putting out a lot of hydrogen ionizing photons, but you're putting out hardly any photons with energies in excess of 4 Rydberg. So I'm going to stamp this model as unlikely. Okay. So this last model that I'm going to talk about, as I said, has exciting implications for reionization if it ends up being the correct model. So this model ties the tau effective dispersion to temperature fluctuations that are imprinted during patchy reionization. So as ionization fronts sweep through the IgM during reionization, they heat the gas to somewhere between 20,000 and 30,000 Kelvin, where the exact temperature depends on the spectrum of the sources and the speed of the ionization fronts. So after the front sweeps through and you have this initial heating, the gas cools primarily by the expansion of the universe and inverse Compton scattering off CMB photons, and this cooling continues until a balance is reached with the photoheating of the background. Now because reionization is patchy, that is you have different regions of the universe experiencing reionization at different times, you've got different gas particles undergoing these heating and cooling processes at different times, and the result of this is temperature fluctuations, which persist for some time until the cooling processes completely erase them. And these temperature fluctuations can actually have a substantial impact on the transmission through the Lyman-alpha forest. So to illustrate that, these two panels show two different simulations of the same patch of the IgM, where on the left, the patch was reionized at a redshift of 6, and on the right, it was reionized at a redshift of 12. This roughly spans the time frame over which we think reionization occurred. On the top, I show the redshift 5.8 Lyman-alpha forest transmission through the same skewer through these two simulations, where the red corresponds to the left, and the blue, which you can hardly see, corresponds to the right. And because this patch was reionized much earlier, it's had longer to cool, such that by redshift 5.8, this patch is colder, and because of the temperature dependence of the recombination coefficient, this patch has overall a higher equilibrium neutral hydrogen density. which ends up suppressing the transmission through the forest by a large factor. And you can see that by comparing the red and the blue curves here. So these temperature variations can actually impact the transmission quite a bit. Now, what does the spatial structure of these temperature fluctuations look like? Can you see this, or it's kind of? That's okay. As long as you can make out the difference between red and black, I think you're good. So these panels show slices through a large-scale rate of transfer simulation of ionization, where the red regions show ionized regions and the black regions are neutral regions. So overdense regions of the universe tend to form more galaxies than underdense regions do. And you can understand this trait by considering a simple model in which you assume that galaxies form in a region that's going under gravitational collapse when the region reaches a certain density threshold. So you can imagine then that regions that are riding on top of a large-scale overdensity, like a mountain, more easily reach that density threshold for forming galaxies than underdense regions, which are in the valleys. So it's the overdense regions that end up forming their galaxies first, and are therefore, so the overdense regions end up being reionized first, and the underdense regions end up being reionized later. So this kind of morphology ends up setting the spatial structure of the temperature fluctuations. So the panel here on the left shows one of our simulations of reionization, where the color scale corresponds to the local timing of reionization, or specifically the redshift at which that point was reionized. So the red regions were reionized earlier, the blue regions were reionized later. On the right, I show the corresponding IGM temperature field at a later redshift of 5.6, where the color scale corresponds to the temperature in units of 10 to the 4 Kelvin. And what you'll notice is that the regions that were reionized earlier end up being colder because they have longer to cool, and the ones that were reionized later are much hotter by a factor of a few or so. And note also that the temperature field is coherent over large scales, 50 megaparsec scale or so, which is exactly what we need to explain the large scale variations in the transmission of the forest. So I calculated the effect of these temperature fluctuations on the Lyman-alpha forest. And so these panels here on the right show some of our mock Lyman-alpha forest spectra, where the blue shows the transmission of the forest, and the red shows the local redshift of reionization. So for example, this region of the forest was reionized redshift 12, this one near redshift of 6. And what you'll notice is that there are large-scale variations in the amount of transmission of the forest. This patch shows almost no transmission, this one shows a lot. In our model, these large-scale variations are tied to the timing of reionization. So again, this patch shows almost no transmission because it was reionized earlier, and so by these redshifts it's colder. And this patch is much hotter, so it shows more transmission. So if this correspondence between the amount of transmission in the forest and the timing of when it was reionized ends up being true, then it would be very interesting because it gives us a way to probe the spatial structure of reionization simply by looking at the transmission through the forest, the variations of the transmission of the forest. So let's take a more quantitative look at these models. Let's look at tau effective distributions. Remember, this is just the probability of measuring a tau effective less than a given value. Higher tau effective means more absorption. Lower tau effective means more transmission. So the black dotted curves for reference show a density fluctuation only model, and these colored curves show our temperature fluctuation models, where the reionization histories, or the global ionized fraction versus redshift, are shown in this inset here. So let's begin by considering this green dash curve, where reionization begins at a redshift 14 and ends at a redshift of 7. So you can see that these green dash curves have a hard time accounting for the full dispersion of the opacity fluctuations. And what that tells you is that if reionization ends too early, then the temperature fluctuations redshift away too much, such that by these redshifts, they're too weak to explain the data. Now let's consider this this blue curve in which reionization ends later at redshift 6, but also begins later at redshift 10, so the duration of reionization is shorter. So again, this model struggles to account for the tau effective dispersion. And what that tells you is that if reionization is too short, the duration of it is too short, you simply don't get the spread between hot and cold that you need. In order to generate a large spread in temperatures, you need reionization to have a longer duration. So this red curve is like our Goldilocks model, in which reionization both ends late at redshift of 6, but is also extended enough to generate large enough spreads in the temperatures to account for the data.
So the green and the blue are essentially overlapping each other all the time.
Yeah, they're very similar to one another.
Yeah.
Yeah. And you can see that they're systematically narrower than the observations which are given by the these histograms. So apparently what you need for this model to work is you need reionization to have ended late. This gives you the more transmissive or the low tau effective regions in your distribution. But you also need large contiguous volumes to have been reionized at early times above a redshift of 9. And this gives you the high tau effective or the most opaque regions of the distribution. So notice that matching this model to the data measured by Becker ends up really telling you something about the timing and the duration of reionization. In addition to this,
Sorry.
yeah.
I mean, to some extent, we kind of knew that reionization isn't just a step function. I mean, like,
Sure, but there is the question of how extended is it, right?
okay, so when you're saying late versus, what's your redshift range?
Yeah, so you know, extended over redshift 6 to 13 or something. We didn't know, actually, we don't really know for certain that reionization had to have ended late, right? That's still an open question observationally. So,
Is it, I mean, it seems like pretty much, there's no Peterson off observed or anything that redshift less than 6.
right, so that tells you a lower limit, right?
Right, so it gives you, it says at least 2%. I understand, I appreciate the fact that it's a very sensitive, although obviously it is like, it's a little particular.
Right, so we knew that reionization had to have ended earlier, roughly speaking, than redshift 6. But it could have, there's no reason why it couldn't have ended at redshift 7, 8, whatever. But what this model is telling you is that reionization had to have ended closer to redshift 6, which we don't have any observational handle on at this moment. So in addition to this Goldilocks model being fully consistent with the latest CMB measurements of the electron scattering optical depth to the CMB, so this has a tau ES of 0.068, I think another key selling point of this model is that the redshift decay of the temperature fluctuations ends up matching on very naturally to the redshift evolution of the tau effective dispersion. And this is remarkable because once you fix the reionization model, there are no free parameters that you can tune to change how the temperature fluctuations decay away with redshift. All of that physics, the temperature evolution physics, is well known. All of the free parameters, all of the freedom is really in setting that reionization model, and then you let the temperature fluctuations decay away, and they end up matching the Lyman-alpha force very nicely. And so there's something attractive about that from a theoretical perspective. And of course, it comes with the added bonus that if it ends up being correct, it provides us with a new window into studying the spatial structure of reionization from the Lyman-alpha force. Okay, so I'd like to conclude by doing sort of a side-by-side comparison of the two models that I think are by far the most plausible. So this short mean free path model, in that model, the voids, cosmic voids, end up seeing a lower ionizing background, both because there are fewer sources of the background there, but also because the absorbers are less highly ionized, and so the mean free path is shorter there. And so the net result of this is that the voids are the most opaque regions of the Lyman-alpha forest. In this relic temperature fluctuation model, the overdense regions are reionized first, such that by these later redshifts, they're colder, and so they therefore have a higher residual neutral hydrogen density, and so the overdensities are the most opaque regions. And so I think this comparison, the reason why I'm doing this is because I think this comparison is very interesting. At first glance, it seems like if these two effects are operating at significant levels, then they probably cancel one another. And so I think we're probably in a one or the other kind of scenario here. But on the bright side, because they make such opposite predictions, other than the tau effective distribution, I think the prospect for testing them and discerning them in the near future is actually quite good. And we're thinking about a number of different ways that we can go about doing that observationally, and I can talk about that later if you'd like. So in conclusion, I hope that I've convinced you that there's something very interesting going on in the high-redshift Lyman-alpha forest, and that trying to understand it could actually open a new window into studying cosmic reionization.